talks in this session. This is the special adjustments section, and we're going to hear some very interesting modeling talks here. And so we're going to start off with Eric Valentine of the Census Bureau, who is going to talk about the effects of different temporary change decay rates in US monthly retail sales time series.
Thank you, Kathy. Good afternoon, everyone. I'm Eric Valentine of the Census Bureau, and I'm going to talk to you about my findings today. This is a disclaimer that any views expressed are mine and not that of the author, and not necessarily those of the Census Bureau. I'll start off with some background on retail sales series data, and then talk about the temporary change regressor. After that, I'll talk about the phase 1 and phase 2 of my research. And then I'll discuss evaluating the decay rate as a continuous parameter. The monthly retail trade survey provides current estimates of sales at retail and food services stores and inventories held by retail stores. It surveys about 13,000 retail businesses and paid employees. The sample was drawn from the Census Bureau's business register and is stratified by major kind of business and estimated sales. My investigation focuses on mainly the monthly retail and food services sales. There are 65 published non-adjusted series and 38 published seasonally adjusted series. An annual review is conducted each year to determine the best way to model the seasonally adjusted series and seasonally adjusted series. Reviewers are recruited from across the Economic Statistical Methods Division of the Census every year to take part. The pandemic effects of the series made annual reviews much more difficult for 2021 and 2022. So the focus has most recently been more on determining outliers in the ARIMA models. Some typical outliers used when modeling retail sales time series are additive outliers and level shifts. Regressor that's less often used to model these series is a temporary change regressor, or a TC. There seems to be some opportunities and growing interest in using TCs during annual review. So I decided to investigate how TCs can be best used in ARIMA models for retail series. The questions I tried to answer are, is there a TC decay rate that is better suited for retail sales other than the default of 0.7? And can we identify better TC decay rates? A temporary change, or a TC regressor, is an outlier or intervention effect that models an abrupt change to the level of the series, followed by an exponential return to the previous level before that change. The return to the previous level might occur gradually or quickly, but not immediately, as in the case of an additive outlier. This is a mathematical representation of a TC. Let's say that T0 is when the change in the series begins. For all time points before T0, the function is just a constant 0. This is because the change has not yet occurred. For time T0 and beyond, the function is an exponential function where alpha is a constant rate of decay that's greater than 0 but less than 1. X13 has a default value, like I mentioned earlier, for the monthly and quarterly series. The default again is 0.7 for the monthly series. The first phase of the research was to take the 65 published retail series and run automatic regular models on them in X13. The series span, the model span was January 2002 to June 2021. Not all of the 65 series have published seasonal adjustments, but for the ones that are, I'm not using the actual adjustments. I'm just doing this for research purposes. I ran the models using the auto model on the model spec, outlier spec, and identify specs. I performed AICC tests for trading day and Easter, and I used the X11 default for the filter. I allowed for mixed models and max orders of 2 for the regular Ermior model and 1 for the seasonal Ermior model. TCs were searched for at decay rates for 4 different decay rates, 0.2, 0.5, 0.7, and 0.9. I had 2 problems though. One was that some of the data files had missing data. The other was that some of the models suffered from regression matrix singularity. These singularities were caused by pandemic outliers in April, May, and June of 2020, where 6 of the 10 occurred in May. This occurred under all of the decay rates except for 0.5. I chose to remove the 13 time series that caused major modeling problems from the analysis, leaving me with 52 series. From there, I evaluated the impacts of each TC decay rate on the regular models by comparing some of the characteristics of the models at each decay rate. So I started off by looking at the proportions and averages of some of the characteristics of the models at each rate. The top 2 bar charts show the average number of outliers in each model at each decay rate and the average number of TCs in each model at each decay rate. The highest number of outliers were detected when the rate was 0.7, but the least amount of outliers were detected when the rate was 0.5. I thought this was interesting because this may suggest that the 0.5 rate may require a less complicated model. Also, the TCs were most often detected when the rate was 0.7, at least when the rate was 0.9. The bottom 2 charts show the proportion of models with 6 coefficient trading day effects and the proportion of models with Easter holiday effects at each decay rate. The proportions of models that detected the trading day effects were very similar, although the models with rates 0.2 and 0.5 detected them slightly more often. The Easter holiday regressor was detected most frequently at decay rate 0.7 and least at decay rate 0.2. Here I have tables of the total Legendre box Q statistics, or LBQs, and the total box Pierce Q or BPQs across all of the models at each decay rate. Table 1 shows the fewest number of total significant LBQs across all of the series. Across all the series occur when the decay rate is at 0.7. However, the fewest percent occur when the rate is at 0.5. And table 2 shows similar results as the LBQs for the BBQs. Here I have tables of the total number of significant lags in the sample autocorrelation function, or the ACF, and the total number of significant lags in the sample partial autocorrelation function, or the PACF. And this is just out of a subset of lags of 1, 2, 3, 4, 6, and 12. I focused on these lags because MRTS consider these to be the most important lags. These tables show that the fewest significant ACF and PACF lags occur at decay rate 0.5, as well as the fewest percent of time series that have significant lags. I considered further research by evaluating the Armour coefficient cross correlations, but they weren't available in X13 to perform difference testing. I also considered using a union of outliers from the automatic runs to reanalyze the models, but this wasn't very feasible. So my method of analysis was to take the set of outliers that I got for a given TC, or TC decay rate, fix those outliers, and then rerun estimation with the other values of the decay rates. And then with no further outlier detection. I call each set of outliers a regression set. I also use the ARIMA form from the automatic run associated with each decay rate. Some of these models did not include a TC regressor in the automatic runs, so they weren't included in this analysis. And from there, I just made several comparisons for each decay rate. First, I compared the AICCs of each time series model of each regression set to see which rate resulted in the minimum AICC and how often it had that result. The rates that produced the minimum AICCs that produced were for each regression set were the rates associated with each regression set. So that means the rate 0.2 was best with the 0.2 regression set, and rate 0.5 was best with the rate 0.5 regression set, and so on. This wasn't surprising, but what was interesting is that the 0.5 rate had the highest percentage of minimum AICCs in these cases with 86%. I compared the model innovation variances similarly, as is the case with the AICCs. The rates that produced the best innovation variances for each regression set were the rates that were associated with that regression set. Again, rate 0.5 had the highest rate of the lowest model innovation variances with 83.7%. I also compared the within sample average forecast error of each time series model of each regression set. This time the results weren't as clear. The best decay rate was not always the rate that was used to find the regression variables. In fact, this was only the case when the rate was 0.9. This time I tracked the counts of the lowest within sample forecast errors. Rate 0.9 was the best for 2 regression sets, while rate 0.7 and 0.2 were each best ones. The counts were not much different, as you can see in the table, so the so-called best rates were not the best by much. The rates that produced the fewest LBQs and BBQs for each regression set were the decay rate that was associated with that regression set. The very fewest number of significant LBQs and BBQs occurred when the rate was 0.7 when using the 0.7 regression set. The fewest number of lags in the sample ACF occurred when the 0.5 regression set was used with the decay rate of 0.5. Also, the fewest number of significant lags in the sample PACF occurred when the 0.9 regression set was used with a decay rate of 0.7. There was some curiosity to see if any statistical test could be performed to evaluate the significance of the difference in the number of outliers at each rate. My supervisor and I consulted Bill Bell. He offered the perspective of viewing the TC decay rate as a continuous parameter. This is something that X13 won't do, but Bill did suggest mimicking this by using X13 to estimate models for a grid of values of the decay rate. I decided on 0.1 to 0.9 incrementing by 0.1. Then I could pick the value that maximizes the likelihood for each set of regressors for each series. There was one series in which no TCs were detected, so I excluded it from the analysis, leaving 51 series. And this was all automated using the seasonal package in R. From here, the idea is to get a confidence intervals for the decay rates. You can plot the log likelihood as a function of the decay rate for each set of regressors. Then for a 95% confidence interval, draw a horizontal line that is 1.92 below the maximum value of the log likelihood function. 1.92 is half of 3.84, which is the 5% critical value for the chi-square distribution with 1 degree of freedom, which for testing a single parameter is the distribution for the log likelihood ratio test statistic. The values of the decay rate where the horizontal line intersects the log likelihood function would be the lower and upper limits of the confidence interval. The values within the interval are the null hypothesis values that would not be rejected by the likelihood ratio test. I reduced some automatic models.
Eric, you have 5 minutes.
Gotcha.
Sorry.
Thank you.
You have 5 minutes left.
I reduced automatic models and regression sets in the same manner as in phase 1 and phase 2, but this time with the decay rates ranging from 0.1 to 0.9. The maximum log likelihood value occurred most often when the decay rate is 0.5. When I applied all 9 of the decay rates to the regression sets, there was a tie at with between 0.5 and 0.6. I did run into a problem when putting together the confidence intervals for the regression sets. The problem that I have is that sometimes there are more or less than 2 intersection points. The number of cases when there are not exactly 2 intersection points is lowest when the closer the rate is to 0 and 1, which is being shown in this graph, and the highest is closest when the rate is around 0.4 or 0.5. The cause of the problems could be that some of the auto models detected multiple TCs. Different decay rates may be best for different TCs at different time points. So I may need to let the TCs have their own decay rate instead of assigning one rate to all rates or to all TCs. I did look at the cases where there is only one TC. Exactly one TC was detected under the lower rates, 0.1 to 0.4, at least under the higher rates. Just out of curiosity, I just looked at the percentage of times a rate was significant for the regression sets it generated. The best percentages were rates 0.4 to 0.7, and 0.7 had the highest percentage. Right, so these results are not fully conclusive, but setting the decay rate to 0.5 may be very useful when modeling US retail sales time series with regular models. The 0.5 decay rate allows for less outliers, better model diagnostics, and may maximize the log likelihood more often than the other rates. Although these findings are interesting, they only pertain to US retail sales time series. Others who want to choose a TC decay rate for their time series might use similar methods to determine what works best for their survey or group of series. Some future work may include letting some of the or all of the TCs have their own decay rate. For a series with 2 TCs, I could try to optimize the decay rate first over the most significant TC, and then I could fix the rate and optimize the rate for the second TC. And this could be something similar could be done for series with more than 2 TCs. Another thing would be to use more detailed values for the decay rate. Special thanks to all of my reviewers and of course Bill Bell for the suggestions on future work.
Okay, we have like 1 minute if anyone wants to ask a really quick question. Okay, our minute is quickly fading. So I think maybe what we should do is go to the next speaker and then we'll have